So you've got a potential divider, right? Now we said that these can be impedances rather than resistors. In other words, they change according to frequency. Well, in this particular case, XL, well, that's an inductor, which is just a coil of wire. And in this particular case, XC, that's a capacitor. Like so. What we can say here is if this is Z1 and this is Z2, now we've moved our potential divider equation into the complex impedance domain. We're now dealing with AC components. But what's Z? What's Z1? What's Z2? Well, look at our picture up there. So in that particular case, Z1 was just R, so we call that R1. And Z2, well, it's a capacitor, right? Right. It's a capacitor. So the circuit we have in multisim is this. But it's still a potential divider. Except this now behaves differently at different frequencies. So if you say to me, well, what's the impedance of that capacitor? I don't know because you haven't told me the frequency. But if you tell me the frequency and you tell me the size of the capacitor, I can tell you what the impedance is through this equation. Yeah. And impedance is just AC resistance, right? What does a capacitor do when it sees AC? All right, let's go back a step. What does a resistor do when it sees AC? Okay, it's a bit of an open question. Some would argue it slows things down. It doesn't slow things down. It just dissipates a little bit of that energy. It lets it through, but it just dissipates it. It's analogous to an electric fire. Okay, so you put electricity in an electric fire, it gets warm, but you've got electricity flowing through it, right? So that's kind of what a resistor does. It just sort of a little bit of heat is radiated out here, if you like. What does a capacitor do when it sees AC? Well, it's a loaded question, because if we see the capacitor here, we see, look at the equation, we see that if we make F very, 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 very big, what happens? What happens? Tell me. It's easy. Hmm? Sorry, say it. It reduces, brilliant. Yeah. So if I make this very big, XC gets very small. Yeah. If I make F very small, XC gets very big. Right, let's write that down. So for a capacitor, if frequency is small, right, impedance is high. If frequency is large, impedance is small. So if I summarise that information, which is what science is all about, right, summarising things, if I put high frequency through that, it lets it through. If I put low frequency through it, blocks it. Lets through, high frequency, and it interferes or interrupts low frequency. Yeah? So let's apply this to, this is an AC signal by the way, yeah? Let's apply this to our circuit. So let's take the example, we're going to put in low frequency. That's our input. Well, what happens? We know that at low frequency, so frequency is small, impedance is high. So this becomes a very, very big resistor. Yeah? So I could just replace that with a very big resistor. So if there's a big resistor here, that's no different to it not being there at all. and all of the AC signal goes out the output. If the frequency is very high, that I put in now, the capacitor conducts everything straight down to ground, which means that its output here goes to 0 volts. Look at the graph on the screen. That's exactly what happens, right? So at low frequencies, the capacitor isn't doing anything, and at high frequencies, the capacitor is conducting point IO3 straight down to ground. So it gives you your 0. Okay? Now if you don't understand any of that, doesn't matter, because this course is about designing PCBs. But it's just nice every now and then to just have a little break from it, from doing multisim that is, and just having a little think about why these things are happening at all. Okay?